Well, hello everyone. Welcome to the 18th webinar in the joint Tran-SET webinar series, which will cover different projects related to innovative applications of 3D printing in construction from three quite different perspectives. Okay, today we're privileged to have three transportation experts presenting in this webinar. We will have three 15 to 20-minute presentations. First, Dr. Ali Kasimia will discuss self-reinforced printing materials for construction 3D printing. After that, Dr. Mohatti will present on the emergence of 3D printable engineered cementitious composites for sustainable and resilient infrastructure. Finally, Dr. Hong Yusu will present on functional cementitious composites for large-scale concrete 3D printing. We will save questions until the end of the three presentations for a 15-minute group questions and answers. You can type your questions anytime throughout the session. And well, now without further ado, I will introduce our first speaker, Dr. Ali Kasimia. Dr. Kasimia is an assistant professor in the Burtis Turner Department of Construction Management at Louisiana State University. His research and teaching activities are focused on construction automation and robotic construction technologies, such as construction 3D printing. His current research projects are focused on the process automation, quality control, and innovative printing materials for construction 3D printing. Before joining LSU, he worked as a senior R&D engineer for 3 years at Contour Crafting Corporation in California. He earned a PhD degree in civil engineering and a master's in computer science from USC. His research activities have resulted in publication of a book, 4 book chapters, and 15 journal papers in the areas of construction 3D printing and special concretes. Dr. Kasimia, I will turn it over to you now.
Thank you very much, Daniel. Let me share my screen first. Okay, can you see the full screen?
Do I have to stop sharing? Yeah.
Perfect. Hi, everyone. I'm very happy to be here to talk about construction 3D printing. The title of my presentation is Self-Reinforced Printing Materials for Construction 3D Printing, and this is a project that we are doing in collaboration with Professor Marwa Hassan, Dr. Arse, and Dr. Nurwand, and several PhD students, including Daniel and Ilaria Luwagiwa and Hassan Ahmed, are working on this project. I didn't know Daniel is going to introduce me, so I included some information here. I joined LSU in 2020, Department of Construction Management, and before that, I worked as a senior research and development engineer with Contour Crafting Corporation, and before that, I was studying in the University of Southern California, where my work was actually focused on the same technology of large-scale 3D printing, and I'm active, in different committees which deal with this technology, including ACI 564, which is 3D printing with cementitious materials. This is an overview of my presentation with 4 main sections. I'm going to go over some of the preliminary results that we have so far on one of our active projects right now, which is regarding this technology and use of self-reinforced printing materials. So I guess all of you are familiar with additive manufacturing, or those desktop 3D printers that are very accessible these days. So the idea of construction 3D printing is basically to scale up those technologies and use it for construction applications to build real scale structures by deposition of layers on top of each other. And you might hear different names: contour crafting, additive construction, or construction 3D printing for the more or less same technology. Here are some pictures of samples which were printed more than 15-20 years ago by the technology contour crafting, which was actually the first one which was invented many years ago at USC. There are many advantages that we are hoping to achieve with construction 3D printing. One of the most important ones is due to the fact that we don't need any kind of formwork with construction 3D printing. And in typical concrete construction, usually 35 to 60% of total concrete construction cost is basically associated with formwork. So by eliminating formwork from the construction process, we can basically achieve significant reductions in the construction time and cost. And then the high degree of customization and freedom in the architectural design is another advantage of construction 3D printing. Unlike a traditional prefabrication, we don't need to replicate a specific design again and again to streamline production or to reduce the cost. Here with 3D printing, every structure can be different without any additional cost added to the project, because basically the robot is doing the job and it doesn't matter if the design is the same or different compared to the last project. And of course, because of the automated nature of this technology, here we are talking about 3D printing of, for example, houses in a matter of a few days rather than several months. And then the environmental aspects actually could be also much improved when we are talking about construction and infrastructure, because of several reasons, including the shorter construction period, more efficient use of materials, and again, getting rid of formwork, which generates a lot of waste during the construction of different structures. As a platform technology, construction 3D printing has a lot of applications in different areas. A lot of people and companies are working on 3D printed bridges, especially in Europe, and more recently in the US. And 3D printed houses, especially for low-income housing, is another interesting application domain for this technology. And then 3D printed towers and disaster relief or emergency construction of temporary or permanent shelters is another area that different agencies are working on. Here are two images related to a project that actually General Electric is doing. They are investing a lot of money on using construction 3D printing for wind turbine tower construction, which would significantly reduce the construction cost compared to the more traditional ways of building wind turbine towers, which is using steel segments in factories and then transporting them to the construction site, which is super expensive. And then in terms of implementation scenario, there are two different mindsets actually. One is that we can use construction 3D printing on the construction site to build any structure in one shot, without any assembly. But the other approach is to basically set up construction printers in a fabrication site in a factory with controlled environment, and then ship those prefabricated and 3D printed elements to the construction site. And each of these two possibilities or scenarios, they have advantages and disadvantages. So basically, there's a lot of debate, and it's an open question for what application, what kind of technology implementation would be more efficient and more useful. On the other hand, changing an industry which has been more or less the same for a long time is not very easy. Supply chain and other aspects of the construction industry have been streamlined over decades, and changing that would be definitely difficult. The other challenge is basically a technical one related to the technology itself. Although, so far the applications of this technology has been so far limited, but still, even in these limited demonstration projects, we have seen many issues, especially with respect to the reliability and robustness of the process and the equipment which are involved in construction 3D printing. And then the next challenge is related to the building codes. We know that we have strict construction regulations, which are of course in place to ensure the safety and resiliency of new structures. But since a new technology like construction 3D printing is still not included in the building codes and design codes, it makes it difficult for agencies and developers to adopt this construction technology. And then the fact that basically we are mostly talking about specific aspects of construction. For example, in building construction, 3D printing is mostly used for only building walls, not, for example, roof construction or foundation, which are still done manually. And the same is true for reinforcement. In almost all of the 3D printed structures, manual reinforcement is being used with 3D printing, which is really doesn't make sense. I mean, the whole point of 3D printing is to automate the construction process. So using manual reinforcement, like what you can see here, some of the buildings which were 3D printed in China and Dubai, they used traditional manual rebar installation. So this last point was basically the motivation for us to start the project at LSU, to investigate some innovative printing materials, so-called self-reinforced printing materials for construction 3D printing, to see if we can reduce or eliminate the need for manual rebar installation in some applications, of course, more focused on the transportation infrastructure. So we have right now 2 active projects. One is more focused on using steel fiber reinforced printing materials, and the other one is more focused on using ECC, which is a topic that Dr. Hassan and others have been working at LSU for years, and they have had an amazing advancement in that field. But today, the focus of my presentation is more on the steel fiber reinforced printing materials. And in our project, we are basically trying to understand, how much improvement in the mechanical properties of printing materials we can get with different dosages of steel fiber. So in this section, I'm going to talk a little bit about some of the preliminary results of our ongoing research project. We decided to use 1/2 inch steel fibers with a diameter of 0.2 millimeter. And these are some steel fibers which are actually used with UHPC mixtures. They are coated with brass, with special coating to improve the bonding between the fiber and the concrete. And then in terms of experimental program, we have selected different parameters like sand to powder ratio. And the idea was that we wanted to see if we can reduce the amount of Portland cement in our mixtures. We are also, we wanted to basically study the impact of limestone. Fiber dosage, I told you some initial testing that we did, we learned that with some modifications to our concrete printer, we can add up to 2.5% by volume of these 1/2 inch steel fibers, which was very exciting. As far as I know, this is the highest amount of steel fiber that have been used for construction 3D printing, 2.5%. So we wanted really to go deeper and see what's the impact on the properties of materials. And then again, based on some initial testing, we learned that the workability range of 170 to 180 millimeter of flow with the flow table is basically the range that we need for our mixtures. So that's what we use for all of our mixtures. And that means that they had the same level of workability, and we had to add higher dosages of superplasticizer to mixture with more fiber to reach that target workability range. And of course, for our printing experiments, we needed a printer. So this is the linear concrete printing platform, which I developed for my PhD students. It has a build envelope of 7 feet by 3 feet height, and is able to handle aggregates up to 1/2 inch maximum size, printing a speed of up to 8 inches per second. And we have some documentation cameras which are automatically triggered when we run an experiment. In terms of fresh properties, directly related to the construction 3D printing process, shape stability is the most important property that we look into. And then some other parameters, even qualitative parameters like the surface quality and the variations in the dimensions of layers, and some more conventional tests which are very useful and important for characterization of our material and finding correlation between different properties of our mixtures, including the workability loss over time, initial setting time, and some rheological characterizations of our materials using an ICAR plus rheometer. I'm not going to present all the results because of the limited time we have, but just to show you to give you an idea of the data that we have collected so far. These are, some experiments in terms of shape stability. This one is a mixture with a better and higher shape stability, so lower deformations, as you can see, lower than 1 millimeter, which is acceptable and very encouraging. And then a mixture with higher dosages of steel fiber that, as you can see, some deformations here we can see and we can measure, which is more than the previous version or mixture. And here are the actual data that we collected for the layer deformations. Here, these are all the mixtures at sand to powder ratio of 1.4 at different dosages of limestone. And looking at each graph, you can see that as a general trend, higher dosages of steel fiber gives us more layer deformations, which is not good, of course. And then also, we don't see significant, at least, improvement in the layer deformations by addition of limestone powder. And here at sand to powder ratio of 1.8, first of all, you can see that mixtures at 2.5% steel fiber were not printable anymore. They were at 1.54, but not here at lower Portland cement content. And then again, the similar observation that we have larger layer deformations at higher dosages of steel fiber. And we think that the reason for that is the increased wet density of mixtures with higher dosages of steel fiber, which also, of course, we measured in the lab, and that is the case. We have the density goes up when you have more fiber in your mixture, which are made out of stainless steel. And the other one is the different rheology of these mixtures. I told you we had a target workability range. And to reach that level of workability for our mixtures with fiber, we had to add more superplasticizer. And actually, when we did the rheological testing, we saw a very good correlation with the yield stress, which is the parameter we expect to be, somehow related to shape stability. So as you can see, the mixtures with these are for rheology tests. We of course didn't include the steel fibers because the rheometers are not basically able to measure the properties of mixtures with the steel fiber, at least. So we removed those, and just to measure the matrix, these are some of the yield stress measurements. And as you can see, for the mixtures with more fiber, because we had more superplasticizer, the yield stress significantly increases. And that could be another reason actually for larger deformations that we measured in the shape stability test. And then on the mechanical properties side, we started with the basic properties of compressive strength and flexural strength. And of course, flexural strength is more important and significant for us because of the target application. We are looking into the tensile performance and properties. And again, to start, we used a single layer specimens which were printed using our printer. And then we measured the flexural strengths at 7 days. And these are some of the measurements you can see as a general trend. Again, with more fiber, we get better flexural strength. Although there is no significant change between 2% and 2.5, but increase basically was significant and obvious. So for the mixtures with sand to powder ratio of 1.4, we were able to get up to 160% increase in flexural strength. And for the group of mixtures with sand to powder ratio of 1.8, we got up to 92% increase in flexural strength only after 7 days of basically storing these samples in the lab. And then, limestone powder is an inert material. So as we anticipated, there was no significant improvement for the mixtures with limestone powder. And we will do more, deeper measurements and investigation into the flexural properties and the ductility of these materials. But we already are seeing some early signs of improvement in ductility. So here you can see some rough measurements we did in terms of the deformations of layers. The orange graph is showing a mixture with 2.5% fiber, the green one with no fiber. And as you can see, not only we are getting improvements in the flexural strength, but also the ductility of these materials, which is a very important factor in the tensile performance of construction materials, are being improved as a result of steel fiber inclusion at high dosages. In terms of the next steps, we want to basically use standard 3D printed beams to measure the flexural strength and ductility of these materials. So we had to, spend a lot of time on the nozzle design and our extrusion system to be able to print these layers that you can see here. These are 4-inch wide, and we were able to print actually very nice and accurate samples. These are 100 millimeter by 100 millimeter by 350 millimeter samples, both with 0% and 2.5% steel fiber that we have been able to print in the lab. And we're gonna basically study the anisotropic behavior of these 3D printed samples in different directions, loading directions, and then as an additional strengthening technique to address one concern, which is the vertical reinforcement and the interlayer adhesion of these layers, we are also gonna add some mini rebars, as you can see here in the image, first manually and then with an automated system to our 3D printed beams, and try to understand and measure the improvements that we could possibly get with inclusion of mini rebars in our 3D printed beams. And in general, in the long run, the focus and the vision of my lab is, moving towards full automation of the construction 3D printing process. I think the automation basically is the key aspect for 3D printing. So automated reinforcement, automated installation, and automated quality control is some of the aspects that we are researching these days in my lab, and we're gonna continue to hopefully make more progress in these directions. I think I'm almost out of time, so a quick summary of our project on steel fiber reinforced materials. We were able to print mixtures with up to 2.5% steel fiber with some level of layer deformations. We are already seeing significant improvements in the mechanical performance of 3D printed materials with these steel fibers, especially when the dosages are higher, at 2% and 2.5. On the other hand, in the fresh state, we see some negative impact of the steel fibers on the layer deformations during the 3D printing state. So that's something maybe we can study more and find some solutions to improve the properties of those layers before they gain some mechanical strength. And before I finish, I want to acknowledge the financial support that we had from Tran-SET. This project is basically fully funded by Tran-SET, and we are grateful for that. And with that, I want to thank you all, and that was my presentation.
Perfect. Thank you, Dr. Kasimia. That was excellent. Okay, now I will introduce the speaker of the second presentation, Dr. Mariam Mohatti. To the it's this one. Sorry. Okay. Okay. Dr. Mariam Mohatti is an assistant professor in civil, construction, and environmental engineering at the University of New Mexico. Her research combines structural engineering, material science, construction engineering, and additive manufacturing to design affordable and sustainable construction materials, structures, and construction practices by using emerging technologies, to enable resilient buildings and infrastructures for future construction on the earth and beyond. She attempts to design practical educational tools and help the public activities by considering engagement among all levels of learners. Okay, Dr. Mohatti. Well, Dr. Mohatti, sadly, she will not be able to present, but one of her students, Muhammad, will present. So, Muhammad, I will turn it over to you now.
Thank you, Danny.
Stop share. Hello, Mohammed.
Yeah. Sorry for the delay. Can you see my screen? Good afternoon, everyone. My name is Saeed. I'm a PhD student working with Dr. Mariam Mohatti at University of New Mexico. Today, I'm going to present our research work on behalf of Dr. Mariam, and it's related to the 3D printing of engineered cementitious composites. So the main aim is to address the problem of reinforcement in 3D computer printing by introducing the self-reinforcing materials. And the material we use, ECC we developed was used by material available in region 6 in cycle 4 and 5 of the Tran-SET project. This is our research team. There are two PhD students and one master student, Amir. We are working on this project, and we are focusing on the fresh and hardened properties of 3D printed engineered cementitious composites. This will be the sequence of my presentation. Firstly, about 3D printing, as you know, is gaining the attention of researchers and industrialists around the globe over the past few years because of its several potential advantages, such as automated construction. It's cost saving in terms where, because the material wastage is also very low, and the formwork, we don't require formwork in the 3D printing construction. So the formwork cost of project can be saved. And also the efficiency of construction is very high as compared to the conventional practices. And we can go for the sustainable construction also too. It is exponentially, the 3D printing construction projects around the world are exponentially growing over the past few years, but still its adaptation at larger scale is quite slow because of several challenges, such as unavailability of standard and codes related to 3D printing. And other challenges include coming up with the mixes that has sufficient rheology and strength in the fresh state. Reinforcement is another issue. As we know, rheology and grain strength has significant impact on the quality of the 3D printing construction. So far, several researchers use different approach to reinforce the 3D printing construction, depending on the stages of the 3D printing, such as before pre-install reinforcement that is installed before starting the 3D printing, during the printing, such as some of them use nails, fibers, and also the mesh insertion reinforcement. And the third is the post printing reinforcement, such as post-tensioning reinforcement. But all of these approaches are still not compatible with 3D printing because with these reinforcing approach, we are actually compromising the automation involved in the 3D printing process. To address this issue, we need some self-reinforcing materials such as engineered cementitious composite, because it has several potential advantages of high tensile ductility, tight crack width, and high strength both in tension and compression. This material is also durable, as durability is another main issue when we talk about the 3D printing concrete construction. In the first and preliminary stage, we worked on the mix design of ECC. Mixing procedure was another challenge to get the better dispersion of the fiber in the mix. From the preliminary stage, we adopted 4 mixes containing the fly ash, slag, silica fume, and metacoiling. And the fiber we used was the PVA fiber, 1.5% of the total volume. This is the mixing sequence, quite long, consists of 3 stages. First stage was like dry mixing of 10 minutes, then mixing after adding water and superposizer, and 10 minutes in the last stage to get the better dispersion of the PVA fiber after adding the fiber. This is the printing system we are using. It's a gantry system with printing limitation of 2 meter by 2 meter of print area and 3 degree of freedom. When we did the initial trials, the quality of printing was not good in terms of suitability, such as dimension consistency, dimension conformity. As you can see, the quality of the printed filament, the dimension consistency and conformity is not good. Also, the surface quality is not very good. In terms of buildability, most of the mixes was collapsed after printing 4 or 5 filaments. Fiber dispersion was another issue that we noticed in the during the mixing. Fiber clustering phenomena was observed, and the shear retention was also very poor. So first we have to address this printing issue with ECC printing. So we come up with using several we call viscosity modifier to get optimized mix, and optimized mix we get with the inclusion of the methyl cellulose in the mix as a viscosity modifying agent. For the fresh property and printability, the flowability rheology was measured by using Brooksfield rheometer. And with the inclusion of methyl cellulose in the mix, the rheology was considerably improved. Rheology parameters such as plastic viscosity, static yield stress, dynamic yield stress, and thixotropy was considerably improved because of the inclusion of methyl cellulose, as MC has the potential to bridge to absorb on the simmer particle and bridge them to lead the improvement of microscopic yield stress. And ultimately, this phenomenon will improve the thixotropy of the mix. For the extrudability evaluation, we printed a hollow square of 60 by 60 centimeter dimensions, and the dimension was measured over the filament at 5 different locations to see the dimension consistency and conformity over the length of the filament. We also investigated the effect of printing speed over the printing quality. When printing speed was increased from 1 centimeter per second to 5 centimeter per second, we observed a reduction in filament dimension, that is thickness and width, from 1 centimeter per second to 5 centimeter per second printing speed. Also, with the addition of viscosity modifier in the mix, the extrudability was considerably improved in terms of dimension consistency, conformity, and surface quality was also very good as compared to the standard ECC mix without any viscosity modifier. We observe that we see that variability in the dimension with the standard deviation. As you can see, the reference mix has more variability in the dimension. That's showing it has less conformity of the dimension. But when we add the MC in the mix, viscosity modifier, the variability in the dimension over the length of the filament was considerably reduced as compared to the reference mix. For the buildability, we printed a 60 by 10 centimeter wall, and we monitored the deformation of the bottom layer with respect to printing each layer on top of it. And for the standard mixes, such as you see FA50 mix, the mix was collapsed after printing 4 or 5 filament when there was no viscosity modifier in the mix. Another thing, we also investigated buildability for 2 times interval. One is the 0 minute time gap, another is 5 minute time gap. So at 0-minute time gap, the buildability of this mix was not good. But at 5-minute time gap, the material was buildable enough to the design dimension. But similar mix with the addition of viscosity modifier in the mix was show a very good buildability and shape retention even at 0-minute time gap, both at 0 and 5-minute time gap. Similarly, another mix containing slag, without any addition of viscosity modifier, the mix was buildable enough, but the printing quality, as you can see, is not very good in terms of extrudability. Similar mix was not extrudable anymore at 5-minute time gap, but when we add the viscosity modifier in the mix, it shows a considerable improvement in the printing quality in terms of shape retention, buildability, and the surface quality also. But another problem with the inclusion of time gap, the interface of filaments get weakened. As the interlayer bond, you can see the porosity between the interface is increased in both cases. This could lead to the decrease in the mechanical performance and also some durability issues after the construction of 3D printed concrete. We also did the fluorescence microscopy analysis to confirm the dispersion of fiber with the addition of MC in the mix. For standard ECC mix, as you can see, there was fiber clustering in the mix, and similar thing was observed during the mixing process. But in case of with the addition of MC in the mix, the fiber was uniformly distributed over the mix, and clustering phenomena was eliminated. To confirm it, we also did this measure distribution coefficient. In case of mixes without MC, the distribution coefficient was 0.68, but it was increased to 0.87, which shows a better dispersion of fibers with the addition of methyl cellulose. And this is the another reason why we get the better quality in terms of buildability, extrudability, and shape retention. In next phase, we are investigating the mechanical performance of the mixes. First, we measure the compressive strength of 50 millimeter cubes extracted from a printed specimen. The mixes with slag shows a better compressive strength as compared to the other mixes. Both had 1.5% and 2% addition of fibers. To measure the flagellal strength, we printed a beam and extracted 40 by 40 by 160 mm prism from that beam to check the flagellal strength of the printed specimen. And as you can see, we also compared the effect of fiber content both for 1.5% and 2% of fiber. And as you can see, there was a considerable improvement in terms of flagellal ductility when we add the 2% of the polyvinyl core fiber in the mix. For the tensile ductility, we use a printed 3D printed dog bone specimen, and the results you can see at 1.5% inclusion of fiber and 2% fiber. With the addition of 2% fiber in the mix, the tensile ductility was considerably improved as compared with the 1.5% fiber in the mixes. In the end, the methyl cellulose was a quite effective rheology modifiers, and it helps in improvement of the fiber dispersion in the mix that ultimately help in improvement of rheological properties such as plastic viscosity, yield stress, and thixotropy. The effect of printing speed, we observed that with increasing speed from 1 centimeter per second to 5 centimeter per second, the printing dimensions such as width and thickness was keep decreasing. So this shows that we have to adopt a optimize printing speed for our mix to get better results in terms of printing quality. In terms of mechanical performance, the 2% addition of fiber in the mix show better performance in terms of flexure ductility and also the tensile ductility. And then I want to thank our sponsor of this project, Tran-SET, and others such as BSF, GCC, for providing material for this project. Thank you very much.
Thank you very much, Mohammed. That was really great, really interesting. Okay, now I will introduce our third presenter. Sorry. Wait. We'll introduce our third presenter. Okay. Now we'll introduce our last presenter, Dr. Hong Yusu. Dr. Hong Yusu is an assistant professor of civil and environmental engineering at the University of Tennessee, Knoxville. Prior to joining Utica, he served 5 years at the University of Alabama in Huntsville as faculty. His research focuses on sustainable and low carbon construction materials, energy efficient and adaptive buildings, and additive construction or 3D printing. His research has been funded by NSF, DOE, Remade Institute, and ALDOT. Okay, Dr. Su, I will turn it over to you now.
Is that okay? Thank you, Daniel. Let me share my screen. Can everyone see my screen okay?
Yes. Yes, we
Okay,
can.
wonderful. Well, thank you. First of all, I'd like to thank the Tran-SET for organizing this webinar series, and I'm very glad to join the cohort of speakers. So today I'm going to talk a little bit about functional cementitious composite for concrete 3D printing. So from the previous two talks that we have heard a lot about concrete 3D printing, its advantage and disadvantages. But so I'm not going to repeat some of already been discussed. But one thing that I really like to reiterate is that this new construction technology provides a very different interaction between the materials and geometric forms for buildings and infrastructures. And because of that, there are new functionalities that can be invoked from this interaction that could involve thermal energy, acoustic, optic, structural, and many more functionalities. So my talk today is going to focus on the utilization of material system in generating some of those functionalities that would be otherwise not possible with traditional construction techniques. So before we jump into the topics, I just want to talk very briefly about what functional cementitious composites are, what functionalities that people have been achieved so far, and what can be integrated into 3D printing. So I'm listing some of the examples of the more well-known examples of functional cementitious composite that would include lightweight and ultra lightweight cementitious composite that include a micro-size lightweight component called fly ash stenosphere that has been studied since about 10 years ago. And we also have a thermal energy storage that's enabled by microencapsulated phase change materials, or PCM. And more recently, that people have been working on self-healing concrete, for example, by adding in microcapsules of bacteria groups into concrete mixtures. And also, it can have some other functionalities in terms of surface or internal curings. While not, there are many things that can be generated through cementitious composite system. Now, if we look at what cementitious composite systems are, right? So we have majorly three different phases where we have the continuous matrix, which is the hydration product of the binder, right? Whether it's in a Portland cement system or it can be gypsum, can be polymer, it can be also lime-based binder, and many more. And also we have this continuous phase, which is our aggregates, and sometimes it can be air voids, either naturally occurred or artificially induced, where I'm going to talk a little bit about later. And then from the previous talks, we have heard a lot about reinforcement, different reinforcing strategies in 3D printable concrete that would include short fibers, that's the most common form, and continuous fibers sometimes, and fabrics. So in terms of the multifunctionalities of this type of material, right? So we look at functional smart cementitious composite that we have many functions that can generate out of the strategy of adding functional additives to the material. That would include electromagnetic shielding by invoking the electric conductive nature of the material. And we can have strain hardening that we have heard about from the ECC and the steel reinforcement, steel fiber reinforcement from the previous talks. And we have damage sensing, thermal sensing, and thermal control. This is where I'm going to focus mostly of my research, my talk today. And sometimes we can achieve mechanical functionalities by invoking internal damping as example into the material system. So if we look at a cementitious composite system, right, it's microstructure, and these are the three different phases that we have talked previously with a continuous matrix that's a hydration product of the binder system. That we have the aggregates, and also we can add in functional additives. In this particular case, it's a core shell particle or particular matter that we added to, or additive that we added to the mix, and shown in its microstructure. So in my group here at University of Tennessee, that we have developed a computational framework that take the multi-scale nature of cementitious composite, and we can basically cross the different scale boundaries in looking at, for example, the microstructure involvement of a cement paste with different cement formulations, the ones that, for example, involve CSA cement or slag or fly ash and so forth to generate a microstructure and homogenize to effective properties that can be passed down to the next level. So this is the part that where we kind of focus our effort on is how to model the functional additives that we add into a cementitious system. For the most part, what we have looked at so far is what we call a core shell configuration, where it has a functional core. It can be as simple as air in the case of lightweighting or thermal insulation, or it can be, for example, PCM or phase change materials for thermal property control. And we developed a computational algorithm that can calculate the effective properties of those functional particles based on its shell property, size, and so forth, and can be homogenized into a continuous phase where it can be combined with aggregates. So I'm going to skip a lot of those details about how this model works, but if you're interested, that I have posted one of our previous publications here that elaborate this model. But essentially, what we look at here is anything that's being added to a cementitious composite, as long as it's in a core shell configuration, it does not have to be a spherical. It can be some other shapes, actually including fiber as well, where it has a, like we said, a functional core and a shell. We find out there is an analytical approach that we can do the conversion from that configuration to a equivalent property in that domain. Then we can use homogenization method to calculate the equivalent properties, whether it's mechanical. In this case, what we have studied so far mostly is elastic properties, as well as thermal properties, including thermal energy storage and thermal conductivity, as well as electric conductivity and so forth. So why we're doing this, right? So we have this computational framework, basically try to use that to guide our material design. In this case, we want to use the microstructures of what we have designed as a cementitious system to achieve certain functionalities, but while, for example, we want to maintain certain mechanical or structural properties. So we kind of went on, did exploration and say, if we want to use PCM or thermal energy storage as an example in the 3D printing, why do we pick this case in the first place? First off, PCM or microencapsulated PCM has been pretty well studied in cementitious systems. Now, people have conducted a number of research about this material. But 3D printing, in our mind, really have provided the niche opportunity for this technology to be transformational in this construction business. Because the way that concrete 3D printing works, I think we have heard from the previous talks, we can strategically place some of those functional additives and some places that where it's mostly needed. In this case, for example, in architectural design, we can look at the orientation of this building as an example. We can look at the solar tracks and the seasons to design where this thermal energy storage capability is needed the most. Or and other places that we can use, for example, stronger materials that has higher mechanical properties in order to leverage those functionality. So we take this as our initial steps, and we want to understand how these functional additives, when that being added to a cementitious system, how that would affect the 3D printing process, and both in the fresh state and also in the hardened state. So the example that we take here is that we take polymer encapsulated PCM, which is the most well understood, well studied functional additives in the thermal space, which basically is a polymer capsule with a paraffin wax core that can go through phase change around the 20 to 22 Celsius degree in this particular case. And this particle comes in a very small size capsules. Roughly the diameter is about 2 to 3 micrometers, and often the material manufacturer would agglomerate them into a large clusters for the ease of handling. So one of the initial things that we want to try here is that if we add those functional additives into 3D printable cementitious material, how that will impact my printability, for example, buildability and so forth, and also the hardened property of the material. So the approach that we take here, we took a functional additive. In this case, it's a micronode powder. And once again, this is a very well understood commercially available PCM system. And we want to add that directly into a 3D printable cementitious mixture. Right, so this is the easiest approach for practitioners, that if we want to invoke certain functionalities, we simply put the functional additives in and add water into the premix, and that's good to go. So this is the kind of the first approach that we take. So the cementitious system here, that we have a commercial 3D printable mixture that's donated from Leakage International to use as a baseline, and then we added a functional particle into it. So and the first step that we basically design the material system and different dosages of microencapsulated PCM and different volume percentage, and then we tested the thermal energy storage capabilities using the DSC scan. So one of the first things that we want to test out there is, based on the volume dosage, how much thermal energy it can store, not only to verify the functionality of the cementitious system or composite system, but also to verify there is not a whole lot of particle or capsule gets broken during the mixing and extrusion process. So after that, we looked at how these functional additives will impact the friction properties that would include the flowability on the top, buildability and printability of the cementitious system based on different percentages of volume loading. One thing that we find pretty interesting is at the lower loading level of those functional particles, that the flowability actually would go up before it slowly comes down. And that is verified by the buildability test, where we can see that with a lower dosage of PCM particles into the cementitious system, that the buildability of that will first increase because of its easier to flow before it goes back up. One of the hypotheses that we have here is that when the volume dosage of those functional particles is low, those microspheres, if you think about what they are in the microstructure, almost act as a lubricant to mobilize those sand particles during the mixing and extrusion process. Whereas when the volume loading of those particles becomes higher, that this will start to form this jamming mechanism to kind of hinder the movement of those sand particles, which will later on lead to printability issues. So this is a printability that the test that we run on those mixtures. And I think the methodology-wise, we have seen a lot from the previous two talks, and I'm not going to repeat. But I'm just going to talk about this conclusion here that if we look at different volume dosages of the micro-sized PCM versus the extrusion rate and speed and print speed that we tested, so basically all the E's right here are the acceptable printing parameters that we find out from our testing. And higher volume loading of micro PCM, that one thing that we find out is it will be beneficial to use higher extrusion rate and higher printing velocity in this particular case, which makes sense because the sextropy behavior of those microparticles can that plays the effect. So, and a higher shear rate, when we talked about earlier about those rheology tests, and higher shear rate, that's where these particles becomes mobile, whereas and lower extrusion rate, that becomes much more difficult to extrude. So I'm just going to show very quickly about the microstructures, about SEM scan that we did. And this is actually a comparison between the casted sample that's on the top and the printed sample on the bottom, where on the left, those are the control mix without any micro PCM that's encapsulated PCMs being added, whereas on the right, those are the we have the microparticles that's being added to about 6% of its volume. So some of the interesting observations that we find out here, and first is that for printed sample, this I think it's a consensus that we have much higher air velocity, the air porosity in the 3D printed mixes, which later on that have impacted the mechanical property, which I will show in a second here. But something quite interesting is because of this lubricating effect that we talked about earlier, those microparticles, those are still leftover clusters, but if you watch very closely, those microcapsules are very well dispersed across the entire binder system. As you see, it's a little bit porous. Those are actually PCM capsules. So because of this lubricating effect, I think that to a large extent, that has helped to eliminate some of the air, large size air voids inside the printed sample, as we can see in its microstructure. So we further tested the mechanical property again. We are not going to talk too much of the details, but we basically tested the printed sample in 3 of its orientations in both X and YZ because of the anisotropic behaviors of printed bead. And we compared the mechanical property versus the cast sample. Again, I think that because of this higher porosity that we observed in the printed sample, we have seen a pretty drastic drop of the compressive stress. We tested further the thermal properties. I'm going to skip that because nothing too intriguing that we see here. But the point here is that the functional particle does not change the thermal property or thermal conductivity of the mixture in any drastic way. And later on, we have run a sort of a demonstration test here to look at its functionalities. In this particular case, it's thermal energy storage capability. So the way that we tested the performance is that we 3D printed a cylinder. That's a hollow cylinder that's using a reference motor, which is commercially available. And then we 3D printed the same motor mixture with 6% of microencapsulated PCM inside. And we placed them inside an environmental chamber, and we insulated at the top and bottom, and we inserted a thermal sensing probe and the very center to measure how the air temperature change inside the cylinders. And then we basically cycle the cylinders in the environmental chamber to test this functionality. So just really quick that I want to show you the result where we looked at here is the surface and also interior air temperature fluctuation. That in the green line is basically our reference mixture, whereas the blue lines are the ones that with PCM. So this is one way of demonstration in, for example, of a daily cycle. If we were to build a building as example, the PCM that's inside the cementitious matrix is going to provide this dampening effect of temperature to improve thermal comfort and also save building energy use. So I'm going to wrap up my talk really quick about some future work that or ongoing work that we're doing here in my group. So we took the computational model that we took earlier, and one thing that we find out is in cementitious system or 3D printing in general, that any soft shell functional additives that we add in, like the polymer encapsulated PCM, for example, is going to harm the mechanical property in a pretty drastic way. One thing that we are currently working on is a different encapsulation technology where we use fly ash cyanosphere, which is a hollow part of the fly ash, as an encapsulation shell. This is a project that we have in collaboration with University of Alabama to use as a capsule to hold PCM materials, and that can be incorporated into 3D printable mixtures. So I just want to show some preliminary thermal test results, and I'm going to come back to this slide and show a lightweight mixtures that we were recently experimenting using similar strategy, but instead in this time we are basically inducing a very large amount of air into a 3D printable mixture. So by far, I think we are achieving the lowest density printable density that we can see in the market right now, or in any literature right now, that we achieve about 0.4 grams per cubic centimeter, which is only less than half of the density of water. And it's still printable and buildable. And one of the other projects that we have ongoing is to use basically 3D printing technology to produce material that is have the capability of sequestrating or absorbing carbon dioxide during the use phase, and also support the biological growth, and we call it living envelope to the building facade. So without overdue much of that, and we have some computational work that's also going on, and this is a previous collaboration and we have with the Chinese university to look at 3D printing to integrate living wall systems into 3D printed buildings. I think I'm probably going a little bit over time, so I'm going to skip this conclusion section. But basically, what we're trying to get a point across is that functional cementitious composite and has provided a lot of spaces and possibilities to 3D printing. So a lot of effort in my group now is trying to basically marry the material with this construction technology to invoke action architectural functionalities that would not be possible otherwise. So with that, I want to present some of those references that we use in this slide, and the students or former students who have worked on the project, Dr. Adam Brooks and Zhenglai Shen, who both worked in Oak Ridge National Lab now, and my collaborators and the funding support from DOE and NSF. And with that, I conclude my talk for today. Thank you very much.
Okay. Thank you very much, Dr. Su. That was really great. Okay, so this concludes the presentation portion of our webinar. Now we will start receiving questions from the attendees. Do we have any questions?
I saw that Andrea.
Yeah, we have one question there for you, Dr. Su.
Yeah, I saw Andrea has a question about the computational model. Yeah, thanks for the question. First off, the multi-scale model that we built is basically an in-house coding that was developed by one of my former students. Whereas the only commercial, or not really commercial, but off-the-shelf software that we use is at the hydration level. That we use the NIST software for calculating or generating the microstructure and the hydration phase. But anything beyond that, we use a in-house code for the homogenization process. I hope that answered your question. Yeah, and I just want to point out that the method is being published. So if you're interested in that computational model, it's in the open space now, that how it was built. So.
Okay, let's give a few more minutes for questions. Yeah, you can share them. You can write them on the chat, or just say, like, ask them directly through here. Okay, we have a question for Dr. Kasimia. Well, they're asking if the presented work is published anywhere yet.
Actually, we are submitting a paper to Tran-SET conference, which is going to happen in August, I guess, in Austin. So that would be our first publication out of this work.
We will also be uploading the recording of this webinar, of the entire webinar, to the Tran-SET's YouTube channel, in case you're interested in going back and seeing a part of it. Okay, we have another question from Hina. This is for all the presenters. She's asking, how much is 3D printing used in the field? We can start with Dr. Kasimia, maybe same order.
So it's difficult to quantify how much. Of course, these are mostly demonstration projects. We cannot say, they are used for everyday construction. But the one which has been most popular has been house construction so far. And then after that, bridge construction, I would say, is the most, in the area with the most highest number of implementations and the demonstration projects. As I said, actually in Europe, a lot of 3D printed bridges have been implemented and are being used by the public, especially in Netherlands. So if you think about the total percentage of the structures, it's a very, very low number. Probably, I don't know, 50 to 100 projects have used 3D printing, I think, so far.
Okay, Dr. Su or Muhammad, I don't know if you, Dr. Su, let's start with Dr. Su then.
Okay, thank you. I think I just can offer my 2 cents. I think concrete 3D printing has been explored for some years now. And from my recent observation of on the practice side, in the United States, I think it's booming very fast in the residential housing construction sector. And there has been a few startup companies that are not quite startup anymore. For example, like ICOM and others has become quite active and successful in the residential construction industry. And I know that DOTs are actively looking at this technology into transportation infrastructures, but there are many other cases that has been demonstrated for example, military use and disaster relief and so forth. As I think Dr. Kasimia has talked about some of those examples in his talk today. But I think it's a very promising field that has seen many practical applications now, and it's growing pretty fast.
Okay, and Muhammad, the same question. How much? Did you hear the question? Is how much is 3D printing used in the field?
Yeah, there are a lot of ongoing projects currently going on in US, mostly in Europe. Europe, you can see many bridge construction using 3D printing, such as cyclist bridge for pedestrians. But still no, we cannot say that all the claims we make about 3D printing are 100% achievable, because still this technology is facing a lot of challenges. It's in development stage. And once the standards and codes will be developed, I think it will be easy to apply it at practical scale.
Okay, thank you. Now we have another question for Dr. Su. Is PCM any better or worse than gluing fibers, and what's the difference?
I think great question, Hina. Basically, the functions that's achieved by fiber and PCMs are completely different, right? So we have fiber is basically a reinforcing system in the mixture with the goal of improving the mechanical properties, ductility, and many more. Whereas PCM, in this case, would provide thermal functionality. So in this particular case of our experiment, it will store the excessive heat that's coming from the exterior or interior environment and slowly release back to the environment. That would help with the energy saving and thermal comfort of the building. So with that said, those two are not it's basically orange and apple, but those two can be married together, because for PCM in general, if we use the polymer encapsulated system that we have in the market now, if we put any higher dosage into the cementitious system, the mechanical property is going to drop or decrease, and that can be partially compensated by the fiber system. That's something that we're looking at to do for the next step. But great question. I hope that answers your question. There are so many additives out there that does different functionalities, and those two are just a little bit different. Then I saw another question from Tam. Did the PCM leakage during the mixing and printing process? Very, very good question. We do not see a significant amount of PCM leakage. The way that we are able to, or we were verifying the process is we would basically take the printed sample of the cement that with PCM inside, and we do the DSC scan of the hardened sample. The reason that we do that is that if the PCM leaks out, some of them is going to react with cement matrix that will basically change the thermal signature under DSC. So we were able to basically observe a very distinct peak and with the latent heat very close to what we think or calculated it should be. So in that sense that we think there is not a whole lot of breakage. And of course, we looked at those samples under SEM as well. And it doesn't really cause any issues in terms of setting during the printing process or after the print. So I hope that answers the question, but the generally is no, we haven't really seen much of the PCM breakage during mixing.
Okay, and I got a question for all presenters. It's a very general question, but where do you see this technology, the 3D printing of concrete, being used, being implemented in the near future? But I mean, in the near future, not like far away. We can start with, in the same order as the presentation, Dr. Kasimia.
Sure. So it's very difficult to say, of course. At least in terms of, with respect to house construction, I can say projects when we are looking into building a large number of buildings or shelters, that would be a good, scenario for using construction 3D printing or prefabrication, where we can set up a construction 3D printer and then build a large number of components 24/7, right? Those are very good scenarios for construction 3D printing. But just imagine building a house, in the downtown, very congested areas. You want to build one house. I think that would never make sense to use a technology like construction 3D printing. So yeah, again, large volume fabrication and production of houses, shelters, and structural elements, I think that's the most likely and realistic and basically the scenario that we can use 3D printing in the near future.
Sounds great. Thank you, Dr. Kasimia. Dr. Mohammed?
What I can see in near future, this technology will be applied in the construction of affordable housing to provide the shelters where the housing is not affordable, especially the shelters for the homeless around the country. And another potential is to apply it in the precast construction. It's very suitable for the precast construction also. Still, there are a lot of challenges we need to address to apply it at practical scale, and I hope some of them will be addressable in near future to apply it at large scale.
Okay, very interesting. Thank you, Mohammed. And last, Dr. Su.
Yeah, so I think in short term, the niche market for concrete 3D printing might be where the human cost is high, right? So we're looking at probably remote areas where transportation or hiring people for construction can become excessively expensive. So that's where we see markets that would justify why the concrete 3D printing technology is being used in those areas. And the second is also, it really changes the way that people think about design, because people have been used to this column, beam, and wall system for over 2,000 years, right? So the structural system of our habitats really have not changed until this fully automated process start to happen. So I think very soon, you know, housings, architecture that is the first market that's going to head, and as people find out more niche applications for this construction method, I think it's going to kind of go into more and more application spaces. Right now, we know it's small, but it's growing. It's growing at actually a pretty rapid rate. But as people works in this area, I think it's going to grow pretty fast.
Okay, perfect. Thank you. Thank you very much, Dr. Su. Okay, if we don't have any other questions, I think we don't. I would like to thank our presenters for their time and technical presentations. I also want to thank all attendees. Please let me know if you have any questions about the webinar series and about Tran-SET. Otherwise, have a great rest of your day.
Thank you, everyone.
Thank you, everyone, for coming.
Thank you.